Hello, my name is Ivy. I'll be the admin for today's session. If you have any question regarding the whole NTW session, just email me at imi@fazmia.com. Bismillahirrahmanirrahim. Pak Atip, you can start the session.
Okay, thank you very much. So the course content for today will be cover introduction to well integrity, and then the philosophy of it, and then the barrier concept, and then the life cycle of the well integrity. So from what position to another, what is the end position for integrity life cycle, and then how we plan for the barrier planning during the life cycle, because every life cycle sometimes some barrier fail, we have to reinstall, we have to verify again, and then consider as safe before we continue. And then we go to our overview of the well integrity management system, the WIMS. I can see that in the WIMS itself, we have considered this is one of the new system application that is being practiced by most companies I think the last 10 years, that will help a lot in terms of managing the integrity of the well. Before, normally it's all done on paper, keeping in the file, and then some records in the Excel format. And then every time we change the engineer, we have problem with database. So with the system WIMS, I think we keep on keeping the system in place, managed by some administration, and then we have data available almost at our own fingertips. We can plan faster and so on. So checklist will be also important to see what are the common checklists required for well integrity. And of course, after we have covered all that, then we try to review what are the challenges. And then at least you can appreciate that to keep the well safe and reasonably under production or under something productive, you need to see the potential challenges so that you know what to do. Verification, normally we have barrier. Whenever you reinstall or whenever you have failure, you have to reinstall the barrier and you have to verify. So we need to understand what are the style or different requirement for verification. And of course, in our oil and gas, we find out that verification is not easy because we have limitation of facilities, and then we are not able to to have something too long to do some verification because it will involve shutting down the well for too long, or maybe we have to pay extra cost for the service provider that provide the repair job. So going to be quite costly if it's too long. So verification had to be done as soon as possible and try to avoid a very lengthy process. Okay, so I think finally we're going to cover more or less the annual pressure management, because this is always the common thing that you see at surface. Because when you monitor a well, for example, the annular pressure will always be the main target for all the fluctuation, the numbers that go beyond your critical limit. You set certain limits, suddenly you go beyond that limit, you are way over it. You might puncture some of the wells and so on. So the casing. So the annular pressure management become one of the key where it's going to be very close to surface. Any failure can be seen immediately. That's why it's become very big subject. Now, of course, we're going to more or less end up our session. So hopefully by covering subject number 1 to 6, we're going to cover about 1 hour. Then we're going to have a break for 5 minutes before we continue for another 1 hour. So it's about 2 hours session for this. Okay. For introduction for this well integrity, you can see that the definition is defined by one of the, I think, Norwegian sector. They have this NOSOC. So definition application of technical, operational, and organizational method to prevent uncontrolled fluid flow to the surface or through surface formation during the well life cycle. Over here, you can see that the definition covers technical, which is something to do with technical and engineering. Operational, something that you do and operate. For example, the well is flowing, so it's operational under the condition of active flowing. Or the well actually having hit by hurricane, so there will be some stresses to the wellbore, to the well. So there will be another check to make sure that we have all the barrier intact. Organization method always be like, make sure what you record is accurate. What is the proof of your accuracy? This organization method mostly dealing with manuals, with recording, reporting, and so on. So this is where WIMS will help an organization to really monitor their wells properly. What happened, in terms of controlling the well, understanding the data, because when anything happen, we are actually we are always, our operation is covered by insurance. So make sure that, when you if you have any issues, then you want to claim for the insurance coverage, the insurance will start to ask you all the sensitive questions about, do you follow your guidelines? Do you have manuals to refer to? Are you going to have a database? How competent is your personnel? All those questions will come in. And we are not able to answer that, then the process of claiming from insurance might be very difficult. So that's why, we have all this element of technical, operation, and organization to be totally in place to be able to be acting like a professional, handling the oil and gas, for the best in terms of revenue coming from the field. Okay, so to prevent well integrity issues, what do we do in place in our organization to prevent such issues? Normally, you have this system, the application that monitor, and of course, to have such a good organization in terms of ensuring the integrity, we need to establish the policy, the guideline, standards, and then what the assurance process, maintenance, of course, the authority, the approval authority also will be part of the policies, where certain level of complexity of integrity have to be signed by the upper management. Otherwise, it can be up to the managers to sign, operation managers. So it depends on the criticality of the process. The policy and guideline will give you the understanding about the approval process that happen. So it's quite a lot in terms of integrity. We want to be professional, get everything intact and properly done. Okay. So this is one of the graph that show how the well integrity is a bit concerned. For example, for the field life, for example, years, we're talking about maybe about 20 years to 30 years or up to 50 years, we can see that the oil production will go up. From initially a few wells drilled, and then production will go up because more wells coming in, and then because of the full swing of the well been drilled, total well drilled, then you have the maximum production. So when you have a maximum production during the field life, that is maybe each time it's about, I think you have the top production maybe after 1 or 2 years of the first oil coming up. The first 2 years maybe you are up to the maximum, and then once you have the maximum production to have the revenue, you maintain the production for maybe another 5 years before it start to deplete. So the production will start to go down maybe 5 to 6 years, and then we go down to the next maybe 15 or 25 years before you have to the limit of production, where the revenue coming from production is overmatching your operating cost. For your operating cost, for example, is about 100,000 per day. Your production might be more than 150, maybe like 200,000 per day production to match with your operating cost, OPEX. So the number here depends on how much is the OPEX for the field. If the field or the platform has certain limits, so we have to match up so that you stop producing when your OPEX is already too high above your revenue of the field lah. So of course, at the same time, you can see that when you're producing, there's a water production, because when you produce from the reservoir will have water, oil, and gas. So based on that, you are going to have all those water being produced from the well, and the production of water will go to the drip string or the production string, and it go to the surface chemistry, going out to the facilities. So the water, actually, every time you have water, you have oxygen, you have corrosion. So that's why, water production is related to corrosion. This is where the well integrity start to be affected. Okay. When you use for producing this well, you also going to produce at high volume. So the velocity of crude will be almost like erosive. So you might say he's some wear and tear when you're producing from the tubing, from the facilities, and you have your wear and tear, so you're actually reducing the wear integrity as well. But at the same time, when you're producing too high, you have some of course, sand itself. Sand is very abrasive, it's going to be a problem. But as you know that when you produce the oil is coming up to the lower pressure at surface, you have the gas oil ratios. The gas is going to be coming up from the reservoir inside the crude, and it can produce at surface. So you have more gas. So gas also will have some speed or some in terms of corrosive material, corrosive element like CO2, H2S. They have to be causing the damage to your well integrity. So from this graph, the conclusion is more like, as you flow the well for a period of time, your question on well integrity become a nightmare. You have to really make sure that everything that is happening during the field life, in terms of the production, the well, the barrier will be intact. Then the well is considered safe in terms of the erosion, the corrosion, and so on. So this is the effect of life. Just like our car, so as you go older, the car actually start to have all the issues with your gearbox, with your drive, your steering wheel, steering structure, and so on. So it's going to be more monitored and repair and maintain, reinstall, of the barrier and so on. So this is about the well integrity of the field of the well life. The next graph is interesting to see that, by time, how many, 20 years, 30 years, you can see that what are the common, the integrity failure that happen during the phase. For example, during the first phase, for example, the early failure will happen because this is the first time you install. Sometimes, you do not know that, you are having some extra stresses in the well. You have more sanding issues in this stage. So you can see the early stage, will see all the early failure. You can start to do the remedial action, do repair jobs in the early stage. That is happen within the range of 3 years. So from starting to 3 years, you can see all the two failure, not because of the system, but because of the specification, or maybe the installation that is not really correct, or something that you installed is not really proper. So it always an earlier failure, and this gives you a lesson learned. So from the lesson learned, the rest of the field life, maybe another 10 to 20 years, normally you have a peaceful environment, or peaceful well condition, where you produce at the best, and then more stresses understood, so you have less problem. But the moment you go and push 15 or beyond 15 years old, the wear and tear start to come into picture, the well integrity become an issue. That is where a lot of repair job will be done within the 10 to 15 years after well production. So you can see the range of time. So it's all time factor, because we are dealing with a long-term well production and facilities. But in our course here, our subject is concentrating on oil, on well only, but not on the facilities yet. So we focus on well. Okay, so this is where we're talking about the history, the record that we have seen from the technical report, from the studies, case study, and so on. We see that, as we go with time, we can see that to manage all those well integrity, the failure frequency happen with time. You can see that you have all the failures coming early in the stage, like I mentioned before. And then once you realize all the understanding with the lesson learned, understood about the problem, you start to have those, increasing with time, because you just know that, the well come in, and then you just waiting for something to come in, and suddenly there's a ad hoc situation of failure. You are in trouble. Then you have to start firefighting. Problem solve, problem solve. So what this trending seems to be studied by many company. We realize that we have a good database using well integrity management system. Then the frequency of failure is almost flattened out, because we monitor the well very closely, hours by hours. So it's like a real time monitoring, and we monitor, we take action earlier. So that's why by implementing the system, the company implemented the system here, we actually reducing the frequency of failure significantly as we go by. And that has been proven, currently most of the company now implement. Even Petronas also impose that we must, every operator must have the WIM system, and then we have to report to Petronas the status of each well every 6 months or every year, to update the status of the field, or of the well, and then the field as well. So you can see in this graph is showing that the importance of having a good database, good monitoring system, good surveilling system, to be able to reduce the frequency of failure. Okay. So, and then of course, now we go to the philosophy of well integrity. Once we understand the concept, the high level, then we go to the well integrity. So, first of all, let's talk about the scope. The well integrity itself has a very wide scope. So you can imagine that, we're talking about, for example, a car. To have a car, you have so many components, and each component, some components very sensitive to time, some components very sensitive to vibration, some components very sensitive to temperature, or usage. Some is not, is sensitive to, of course, distance, and of course, equal to time. So this is more or less same for well integrity. We have well operation that are going to be handled in terms of integrity. The ownership and the handover must be proper. Otherwise, we are not able to understand what stage the failure start and what stage is the weak point, or the failure to monitor. And then, of course, we must understand that we must have competency people, and that competency not only refer to the experienced people, but it's going to refer to the what call it the training itself, as well as the policy of the company. Even sometimes we engage third party consultant to help us. So it depends on, but anyhow, the competency always become a very critical subject, that we always hire the right people for the right job, and then you must be constantly, monitoring high quality jobs to be performed by this gentleman. Orchestra memang have procedures, corporate operation we memang have procedures so that everybody can check, understand what to do, what is critical, and so on. So at the same time, corrosion and erosion management become important. So sometimes most company they will hire corrosion engineer just to do that. So if you have a big company, if it's a small company, normally one of the engineer will be assigned to be able to monitor corrosion with the help of the third party. For big company like Petronas or like Shell, they have their own corrosion engineer that will help to really identify all this well integrity properly. And then, of course, we are talking about the scope of validity to cover tubing and casing, because this is the main conduit for the production. This is the life. If they fail in casing, the well have to be shut down. The fail in tubing is also the same. They will have to be shut down. And tubing, since it carry high pressure fluid in the tube, any leak will cause and some excess, some stress, excess to your well bore. So we have to make sure that tubing and casing are intact when we produce. So reporting all those behavior or casing, the tubing, the annulus, the condition, we do survey every time to know the thickness itself, whether the thickness of tubing is reducing or not. It's all done by the survey, with special survey. So we have a lot of tools to make sure that we have a good integrity, good check for all our components. So well intervention is, of course, we want to understand who's going to be assigned to have that well, and then this this owner of the well will be able to assign certain requirement to repair to this particular well. Same thing, you need a very experienced people, competent people to be able to do the right intervention and be effective. Sometimes you do not know what you're going to do, then it's a waste of time, because you do try to repair, but sometimes you introduce more problem. So that's why, where I think competency or the personnel is quite in well interventions part of it, office. The next one is the system, the database. So, and then the recording, the application, when the WIMS itself, we call it WIMS. And then actually it helps the company to have a consistent record, consistent style or reporting. And then there always be a requirement for us to fulfill the requirement for certain forms, certain record, and certain checklists. So this system helps the company and the personnel to understand what is done 5 years ago, 6 years ago, 3 years ago, 1 year ago, and so on. So we know the history of that well, and then we can even capture some of the lesson learned. And what we are doing next is going to be much more effective and very conclusive. So that's the system. And well barrier elements is another topic that is important, because even you have all the fancy things, you have all the experience, but we must understand that well barrier is a special element that need to be properly selected. Because if the company have no proper guideline for selection of barrier, then there might be some mistakes by certain engineer to not to procure some of the some of the barrier that is not suitable for the field. For example, if the field do not know about the existence of lead, and then the existence of H2S in the later stage of production, then some barrier will fail earlier, and then they are not ready to really handle the situation of leak barrier, and so on. So another one is standard. You see that the standards coming in by each company. Everyone try to have their own company. In Norway, they have their own NOSOC system, where they have their own system. In America, they have also some API guided for the well integrity. And for us, Petronas try to have their own, following some of the guidelines from NOSOC, from the API, combination of that, and just to suit the requirement of Malaysia. So Petronas also have some guideline for well integrity. Yeah? So issues, normally we're talking about, to understand, we have to know about the schematic drawing, should be updated all the time. The problem that we always have is that, some of the well schematic have been kept on board the platform itself. And then every time that we do some minor jobs, sometimes all the records offshore on the platform is not updated. It's always updated in town. That's a problem. And then, of course, you're comparing a different situation. When you want to discuss, you're referring to a different drawing. One is updated, one is old. So it's a lot of confusion. So at the same time, well issues, you have to do a periodic inspection, systematic inspection, corrective action, and so on. Because without all this requirement, then you're exposing the well to the unknown status. So every time we come back to well WIM system, where we record most of the work done. Okay, there's a big assignment for the well integrity itself. Okay, so I think once you have the philosophy done, you can see that integrity refer to maintaining full control of fluids within your well. So fluids here is hydrocarbon, and fluids also can be the completion fluid and so on. But I think more of the pressurized system is because of the fluid is under pressure coming from the reservoir and flowing up to surface. And then in order to prevent unintended fluid movement or losses, containment, then of course we need to have all this with philosophy, integrity, a guideline to monitor that. Any failure, you must be able to record earlier. Some well, they have sensors to be installed downhole, to be able to observe the pressure system coming out from offshore, from bottom up to surface. At surface, there will be another sensor to check whether there was any fluctuation of pressure and temperature, or is there any differences in flow rate that can lead to a potential leak within the surface system. Okay, so operator must define its commitment and obligation to protect. So this is more or less the concept of well integrity, that we want to safeguard the health of the people or the environment. We must make sure safety for the people working around the area. At the same time, I make sure that we are protecting the environment when we do all these procedures. There's no leak, no spill, no gas emission to the surface, and so on. At the same time, as said, actually, because if any failure, it can create some nightmare of fire and so on, that will actually destroy your assets. So it actually, well integrity help a lot to reduce the impact, commercial impact, and the safety of the people and the environment. Okay. Any question? Just put in your chat box. Then we try to answer one by one, because I think you will come across some of the of your experience, even on the so normal life. For example, you want to do car maintenance, and then there's certain area that you do not know what should you do. So we always try to relate those situation in the real life. So I think what happened for offshore, what we were doing is on the professional style. So we try to apply whatever we do offshore professionally, high level. We try to apply what we are going to do on everyday life, so that we can try to to gain the knowledge of how to realize the importance of well integrity, or whatever asset integrity in our life. Okay. So I think on the impact of well integrity failure, in the oil and gas, we have seen that history or records of failure, is very amazing. It happens every 5 years, sometimes 6 years. We have big major disaster in the field. I think the current one we have Mokondo 2010. So I think the last one also there's some other event, but 10th now is 24, so it's about 15 years. So 15 years until now there's nothing happened yet. So Mokondo oil spill is the worst nightmare in the world. happened in the Gulf of Mexico. So, I think they have BP have been paying a lot of this repair job, try to environmental impact to go back to start to clean up all the oil spill, huge oil spill, and then to do cleaning up on the beaches and so on, pay the compensation or insurance for the people and the damage to the property lah. Piper Alpha is quite long ago in North Sea. So we have incident where, the flow is coming up to the shore. And then, of course, suddenly there's found some failure that happened in the platform because of the integrity, well integrity or electricity integrity. And then they are not shutting down enough time because they are still thinking about it's only one line going to the platform and the rest should still go to the shore for production, and they are worried about losing production. So then even is on fire, but still is still in from other field, then the fire going on, it just burn down everything to the ground. So that's incident of Piper Alpha. Okay. Then there's impact a lot. And then of course, the next subject we're going to cover called safety critical element. So for a safety critical element, you can see that, critical elements always that it relate to the safety and the integrity. So what is going to refer to is that when it fail, then it's going to give you a problem. So SCC or a safety critical element is individual piece of equipment, a control system, or individual protective device which in the event of single failure will cause direct cause incident or result in hazardous. So this is like, for example, like it's almost like a last line of defense. That's the definition, last line of defense. So when you fail, you start to see the result of failure. So normally, once we have this, we in our system, in well integrated system, we want to install another control system. So now we have second. This is primary. We still have a secondary where if this fail, then the secondary barrier will stop the gas from creating a lot of issues. So that's why when we talk about the barrier, we always propose a two barrier system. So one secondary, one primary. So if one fail, we still have another one as a backup before we plan for the remedial action. Okay, this is the safety critical element. Okay, now we go for the well barrier concept. So for the well barrier concept, you can see that, we have to understand what are the requirements, what are the normal thinking about the well barrier. So the well barrier planning and verification, we cover a long list. This are in general. So we start with for the barrier planning. So what is the well condition, and then when we find the barrier, it's going to be secondary, primary, or going to be like it's for long term, it's short term, and so on. And then we need to have the authority, technical authority approval, so that whenever we plan for a barrier, the expert advice, expert review have been done, and then we are putting up the right process, and then normally the confidence level will be high, and then we know that we have done a good job once we have the authority approval, okay, technical. So some company, they have their own technical authority in-house. Sometimes we ask for third-party expert and they have the authority and have the certification to authorize. But normally for big company, they have their own technical authority that's familiar with the company policy. The number second is the barrier itself. So, with like two barriers as minimum, like we discussed, we have two barriers. One fail, we have another one on standby. So we have to identify, define, and express responsibility. Normally, the people in charge, who's going to sign, who's going to propose and sign. So there's a few process for understanding the level of responsibility and the approval process for the well integrity. And then at the same time, we have another critical number three is MOC, management of change and exception. Because when we do the well integrity, sometimes you want to propose something that is not achievable because of the constraint, because of limitation of the well. So we have to provide some of the proposal that not going to meet the normal requirement, but still it's still possible because we have option, we have reason. For example, some of the chances of failure is very minimum, or some of the leak is still acceptable. So you can still continue with your plan, but you have to really justify and put the MOC, management of change, so that the people understand that you are going to go a bit deviated from your initial program, but you have all your risk assessment done, you have the option being put in that is still manageable. Then if anything happen, you have the backup plan. So that's the MOC. So number 4 is certification, maintenance, and traceability. So for barrier, you have to see that certification is always like, for example, when you have a certain element coming up, barrier element, they will come up with the specification, certification into the quality of the material and the system that is being checked for stress. In terms of life, maybe being checked for maybe it lasts for 20 years or 50 years. Some certification will show you the numbers that will help you to really realize the reliability of the barrier. Some barrier can only last for 2 years, some barrier can last for forever, so we do not know. So it's possibility lah. For maintenance, of course, you try to see what are maintenance to be done so that some of the barrier need to be maintained so that it can be almost like extending the life of the barrier. Traceability, we'll talk about how we trace in terms of anything that you want to run in, you must be able to trace the position, the location itself, and then you want to know that this product is coming from certain area. For example, if you're coming from UK, there's a certain numbers or tracing number, part number, that if anything you have problems, you can trace back to the manufacturing to understand the QA/QC process and then the material use and so on. So that's the traceability. Compliance audit, there's always be some audit coming in just to make sure all your certification, your system, your selection, your guideline procedures is being followed for your installation of your barrier. Reporting, like normal, you have to be report properly. Number 7 is barrier failure. So if any barrier failure or loss, you have to stop the activities on that particular well. Sometimes that particular well also affect the total platform. So that's why whenever we have a barrier failure, sometimes you shut down the total platform. That is where the loss will be huge because the revenue is coming from the production, and when you shut it off, it's going to take time to really pick up the platform, the platform to production again. So that's why any barrier failure or losses, we try to see, it's going to be limited to certain well. That's why when we install the barrier, when we install the system or the well production, we try to make sure it's a failure of one well, it will not affect the others. But always be, we have seen that whenever there's a failure, it always be so big that will impact the total platform. So we have 20 wells on the platform. One failure can cause a shutdown of 20 wells. So that's why, with the proper design of the facilities, with design of the protection, we should be able to, to manage well by well basis rather than the total platform. So it depends on how much we have the idea of, or the flexibility to have the option, barrier by well, other than one barrier, one well failed, that everything be shut down. So in terms of our experience, normally we see that some of the incident can be handled one well to well basis. So you don't need to have a shutdown. But in most cases, like a small platform, our simultaneous operation system, our management system contingency plan is quite limited. So one failure means that one well failure will have to cause the full shutdown of the platform. Okay, now after losses, the operating procedures. Because
Okay,
you're displaying.
there is one question
Hmm.
on the barrier loss
Okay.
from family. He would like to know a little bit more about what are the barrier against to, is it like is it a kick from the well? I think we probably would need to clarify a little bit. The barrier is against the pressure from the commission, probably what I think.
Yeah. Okay. Yeah. Okay. So far, in terms of the well control, there's two phases. For example, when we are drilling, we're talking about drilling a well. So drilling a well, we have a casing being set up. We tested the casing when we bump the plug during cementing. So we have tested the barrier. So casing is a barrier. Cemented casing is a barrier. And then we install BOP on top. So it become another secondary barrier. So we have a primary barrier casing and we have a secondary barrier of the BOP, a secondary barrier. Then we also introduce the primary barrier like the hydrostatic mud. It's one of the temporary barrier. We call it temporary barrier of drilling mud. So we have these three barrier, casing, cemented, and we have the BOP, we have mud. So there's a three barrier when we drill the open hole. So for example, you lost one. For example, you have a casing leak. Then you lost one of the barrier. Then of course there's the control of the well is still there because you have hydrostatic pressure. You have BOP, so you still can continue to kill the well and do the repair job. Meanwhile, so what we do actually, we have a leak in casing. We kill the well and then we put in our normally we call it bridge plug. We pull out the casing, running and set bridge plug, and then we repair. So we isolate the bottom part of the open hole from the well control issue. We repair the casing. Once we repair the casing, we drill out and then drill out the bridge plug, continue drilling ahead. So that's the way of managing the loss of barrier. If you are drilling open hole, suddenly you have losses. Of course, you lost the hydrostatic head. So what you lost your static head, you still have casing to protect you, and you have your BOP. So you still have the barrier that will continue or be able to be used as your well control system, control the well, and go back to your normal barrier. So it's about 3 barrier when we drill a well, something like that. Okay, Fahmi. So I think just talking about, I think it's interesting to see the barrier itself because in our barrier we talk about producing well, we're talking about drilling a well, we're talking about uh, plant abandonment. Plant abandonment, we must be able to install the proper barrier so that it will be live for long. So for plant abandonment, normally we're talking about assuming the well should be lasting for 100 years. So we put in a proper barrier to be able to last the well isolated. Because we are not able to access the well anymore. See, permanently plugged environment, it should be live for 100 years. So we pre-plan all those barrier in place, hoping that it will last for 100 years. Okay. So compliance to two-barrier concept. I think this is like I mentioned to you. I think Fahmi mentioned about how we're going to manage the losses of barrier when we drill. So this is where we see this requirement coming in to understand the two barrier for the completed well. So when the well is producing, we know that the stresses is in the tubing. The tubing we have pressure, we have temperature, we have the combustible unit liquid. The gas or the oil. And then for example, if there's a barrier of failure, then we should be able to manage those failure and then repair the job and then get it back to the two barrier concept. So for example, in our case here, you have the primary barrier fail, like the tubing leak. When we tubing leak, of course, the pressure in the tubing will be transmitted to the annulus behind the tubing. So we have the pressurized tubing, and then of course the annulus as well. And this is where we're talking about we cannot produce because we're going to have high pressure annulus, and then we have to really repair the leak in the tubing before we can continue producing the well. This is where a single well can be isolated. No need for us to shut down the platform. And then, of course, when we come in with the wireline work or maybe some core tubing or whatever, to do the repair job, normally, it's going to be a patch. We're going to run a tubing patch where we set the patch between the weak zone. And then, of course, when we perform the patch during the wireline, then we continue producing. That's the situation of repair job, simple repair job. But if there's for example, a puncture, a cut, or maybe the tubing is parted, of course we cannot use patching. Then of course the only solution is to call for a hydraulic over unit and now kill the well and then pull the old tubing and rerun the completion, tie in back to the old cut well. So that's how the repair job, which is more time consuming, expensive if it is parted. If it is a hole, then normally we run wireline to run the patch, so to isolate the leak with the patch, like a set of packer. Okay, that's how we have to have two barrier to be able, one barrier will give us opportunity to install a temporary barrier like wireline BOP and then continue with the repair job. So we still have the two barrier. After we have one failure, so we reinstall another barrier, which is the wireline BOP, and then of course the kid fit before we do the repair job. Okay, I have a quiz here. Is it possible to have one barrier placement in known and safe condition? there's a question like, can we have only one barrier if we are very familiar with the area and it's safe condition? So what is the expected answer? So one barrier, if we know the area, we know that the pressure is still there, and then everything we say, even though it's leak or patted, we have the Christmas tree, or we have all the safety valve and so on. So in our production, you can see that we have the barrier when we're producing well. We had the barrier of the tested tubing. One is tested tubing, and then we have the barrier of another barrier called triple SV, and then we have the Christmas tree set at the top. So some company will not consider triple SV as a barrier. So you only have two barrier, which is your tested tubing and then your Christmas tree. So there's two, but still you can work it out. But in some cases, some company consider triple SV as your another barrier, secondary barrier. So if that's the case, then you still consider, like for example, you have a leak BOP, a leak chemistry, we can still do the repair by shutting in the triple SV, pull in the one-way valve across the chemistry, and then across the wellhead, and then you nipple down your chemistry and do the repair. All those kind of things possible. So, however, it all must be come up to the definition of two barriers. So, if you can consider that two barriers will be in place, then you are ready to do a repair jobs, and then even to continue producing the well.
Pak
For
Tip,
example,
I would
in
like
some
to just
cases, we don't want to lose the revenue. So, even though there's a failure in your triple SV, but because we need to produce the well for another 2 days, for example, to make up to the production, in some cases we can ask for MOC because the valve itself might be not able to be closed, for example, because of some failure. But still, you should have another barrier like Christmas tree and your tubing to be able you to continue producing, but not for too long because it's only for temporary situation. So it's all based on the MOC that you're going to put in place. Okay.
Pak Tip, can you hear
Done
me?
that. So well
Pak Tip,
integrity life cycle. So this is another one that we try to understand what life cycle. I think we have covered that. It's going to be from year 0 to year 40 or year 50 years. So the life cycle. Okay. So there's three main pillar in the well integrity life cycle. We have the technical issues, with safety, and then we have management. So for technical, when we talk about the life cycle, we must have a proper well design to be able for the well to be designed for 20 years, 30 years, or 50 years. In some cases, mostly when we ask the engineer, when you design a well, how long actually you expect the well to life, to survive? So of course, we know that in our planning for the field development plan, the well is expected, or the production from the field is expected to go for 25 years. That's as per the PAC agreement, 25 years. So we try to organize some like 25 years. And then might be, Petronas may say, why don't you extend another 5 years? So we're talking about 30 years. So you design for 30 years. The issue is always that how you are guaranteed that going to be 30 years, because you have to know the history of the corrosion rate or the erosion rate. And then in terms of the pressure development, you're going to be like pressure increasing or reducing. So in our normal common production life history, we can see that pressure is going to go down. It's going to be depleted. So we're expecting pressure to go down as the field proceed. So based on that, we're talking about, if possible, the design will cover that range based on that requirement for reservoir. Of course, once we know, for example, the well design, the thickness of the casing, the material type should be tallied to the environment. Even pressure is down, but still you consider that you should be able to maintain that safety factor or whatever in your competition. So,
Pak Tip, sekejap. Check and see the audio.
well done.
The audio, because I just wanted to make a bit of a discussion because there's a question over there from Fahmi, and then he did mention something really interesting.
Yeah.
If you only have one barrier, what is it going to be? And probably you would need to talk a little bit about mechanical barrier versus hydrostatic barrier, where something that you can rely on, so on and so forth. Yeah.
Yeah.
Thank you.
Okay. I think now the question is always it's interesting question because it happened in many occasions. Yeah. For example, some company define the hydrostatic barrier is only valid if you have something solid to prevent it from dropping. For example, you have hydrostatic, is considered overbalanced, but the issue is always that you don't have any something to stop. For example, if they have a loss correlation, if there's something happening that you weaken up some of the formation because of the reaction with the water and so on, then you take out the fluid, the hydrostatic will be lost because there's nothing to stop it. So in some company define you only consider hydrostatic head as your valid barrier if there's a solid foundation at the bottom. So that's why in our case, we always consider hydrostatic as a temporary barrier. In other words, it's subject to condition. If the well start to to flow, then of course hydrostatic is going to be almost like our tools to protect to stop the flowing of hydrocarbon. But if we are dealing with losses, then we're talking about loss of hydrostatic, and then the losses will be our concern. But because we are talking about having a better control, like we always have another weak points at the bottom, so normally hydrostatic have to be always be on our side, so we don't lose the hydrostatic because of losses alone, but we should be able to top up the hydrostatic and try to do like spotting up SCM and so on to reduce the losses. But if the losses continue, then your hydrostatic barrier not become a secondary barrier anymore. So your temporary barrier is actually failed. Then you still have to more or less like dealing with something like circulating the hole under dynamic condition for ACD, or you have to really start to kill the well using the driller's method, and then you are going to place up with the right mud and so on. So it's true that hydrostatic head is only valid if it is having a solid base. But in most cases, like in my cases, I always refer the hydrostatic is still a temporary barrier, and then we handle losses or flow independently because because without that criteria, normally you are not able to drill because if you ask for two barrier, and then if hydrostatic is not considered a barrier, you only have the DBOP and then even the cemented casing. Some company will consider that cemented casing is not a barrier because we have open hole down there. So it's subject to condition. But for us, for the safety of the people and for the hazard, for me, I will consider cemented casing tested will be considered as a barrier because the formation at the bottom is another area of concern. So we are concerned about the casing and upwards, where we have the properties, the asset, and the people. Of course, managing this problem at the bottom in open hole is can depend. It depends on so many things. Like for example, we have well control, uncontrolled blowout. So normally we try to make sure we kill the well by injection, or we allow the formation to collapse and kill by itself. So there's so many possible scenario, but as long as you discuss about the concern, then all the contingency plan, understanding about what your strength, what your weaknesses, and manage that accordingly. Okay, I think I hope I will answer that only. So I find like a picture. Then what else? What else? Yeah, backup, extra progression, and also nice to nice pretty. Okay, no worries. I can scroll down. Okay, sorry. Just to look at some of the question again, maybe I answer halfly, yeah? So okay, I can pay the backup precaution. What else? Yes, okay.
I think you have answered
Okay.
most of them, but I think it's an interesting part that we would like to further discuss lah. Because well integrity, to me is a topic that keeps on evolving, and it takes a look at the basic principles of understanding what it is all about. For example, lah, if I may interject a little bit, yeah, Pak Tip,
Yep.
for example, lah, hydrostatic pressure lah, that comes together from your are drilling fluids. And that drilling fluids, inside there, there's barite or whatsoever. Whenever that your barite settles, that drilling fluids no longer hold the same amount of hydrostatic pressure as what you initially have. So that's the reason why when we talk about hydrostatic pressure as the well integrity or barrier, that is something that people always question. Yeah, a mechanical barrier has always been the strongest one as well. But again, it really depends on how comfortable you are as a designer of the well and the operations itself. Yeah, as Pak Tit mentioned just now as well, if you have the well that you already know what is going on in that particular well, so you kind of like have over optimism. Remember what I said just now. But whenever that kick happens, it the well is going to go through another different kind of environment altogether. So just be careful with that. All right, thank you. Back to you, Patit.
Yeah, thank you. Okay, just to me to summarize again, as I think we're going to cover that if I miss it. But anyhow, let's mention about when we talk about well integrity, we have a few phases. Like for example, you have a drilling phase where you drill a well. You need to have the well integrity, the two barrier. And you drill with the BOP, you have drill with the cemented casing, you have drill with open hole, we have losses. So your barrier is always around the cemented casing and the BOP. And the hydrostatic, like I mentioned, it can be temporary because there's no big support, no mechanical support, so it's not considered a barrier. But for me, I see consider as a temporary barrier, which is part of the parcel of managing the barrier that we need to control. For example, you have, for example, the well is stable, open hole is stable, and then you BOP leak. Then you say, oh, I have no barrier. No, you have cemented casing one, and you have your hydrostatic. But your hydrostatic is temporary, so you have to do the BOP repair as soon as possible. Or, if sometime management will not agree, see, they say that no matter how you are stable, you only have two barrier, and then if one barrier fail, then you are gone because the BOP is just being removed. So this is where we need to put a mechanical barrier, bridge plug, about 1,000 feet or to 1,000 meter, and then you can nipple down your BOP because you have another temporary barrier to do that. And temporary barrier during operation, bridge solid barrier is considered okay because you can test the barrier after that period of time. For example, you repair work will take about 24 hours. You tested the bridge plug as barrier, then this plug should last for maybe for 1 month, but you just need it for 24 hours. But it's different from completed well. Producing wells, we're talking about producing wells more than maybe like 10 years or so on. So when you put a barrier, mechanical barrier is only temporary. It's not considered as a permanent barrier, and it's not considered to be one of the two barrier because it can start to be corroded, it can start to be unlashed, it can start to be leaking after some time. So that's why it's a different scenario between drilling, which is short-term basis on certain barrier, and for producing well, which is totally a different thing. And the same thing like when you want to P&A the well. P&A the well talking about we have to get rest to the well for 100 years, for example. So you have to put in something that is permanent. So industry accept that cement is considered a valid barrier because it can last for 100 years. But you put in bridge plug, it's not considered as a barrier because it can deteriorate, it can have the field life. So that's why during P&A, it's a totally different ball game, different definition of well barrier. Interesting, eh? Many variables, many conditions. Okay. Now let's go. I think for the integrity surveillance, as you know, when we put in the integrity, we have to put the surveillance to the well, understanding the strength of the well and the weaknesses. So like I mentioned to you, we have the drilling phase, different integrity surveillance, and then we have production phase, and then we will do repair work. When we do repair work, we pull out tubing, we have barrier or cemented casing, and then we pull out tubing, then we lost the tubing. We have, of course, some brine in the whole production packer fluid is higher than your normal pressures. This is another barrier, but of course, if it is perforation there, then is open to the hole. If the operation is a weak zone, then you lost your hydrostatic. So the barrier condensation on these faces it can be different. So walkover is PNA lah. So you can see that wave integrity ensures comprehensive capability in preventing uncontrolled hydrocarbon leak. So it's always be referred to hydrocarbon leak. So whether you want to do any repair work, you are going to expose to the hydrocarbon leak. Whenever you want to do pulling out tubing, you want to replace casing, repair casing, repair your BOP is all dealing with potential hydrocarbon leak. So that's why we have to consider what barrier to really stop the potential leak lah. Two barrier concept. So during production phase, integrity is achieved by means of barriers. So we have casing, cemented casing, tested tubing. Because if you cement casing and you don't test, then it's not considered a valid barrier because valid barrier is only when you have tested, okay, then it becomes a valid barrier. Same with tubing. So when you install tubing, you need to test the tubing to the reservoir pressure or plus maybe 300 psi, then become a valid barrier and so on. So you have to see that barrier is only valid if it's been tested. Otherwise, you have to explain a lot how you have that confidence that the barrier is going to be reliable without testing. Okay, reliability of barrier element is subject to technical judgment based on the best industrial practice and so on. So reliable database for well component and how the subject accuracy of the subject, WIMS also will help to establish the record of this. Because when we have WIMS, let's say we have 20 wells in the field. So each well we give you some understanding about the potential barrier of the field, the strength of the field, and so on. So that's why in some cases, for example, the verification asks for the pressure from bottom. So just imagine that you have your tubing. You have your tubing, and then suddenly, your tubing have to be tested from bottom because the testing will be top testing and bottom. You have to have a pressure from bottom and also have the pressure from the top. So sometimes you only have the ability to test from top. You are not able to test from bottom. So this is where the judgment will be like, okay, the top pressure reliability or okay should be considered like okay at the bottom. But some company they still consider a remark, that is not fully tested because they need to test it from both sides, up and down. So that's always an issue. But of course, in some cases, we ask the manufacturer to test dekat field, dekat lab. So now they go to the factory, we put a system, we test top and bottom. Normally it's okay, at least you have the evidence that if you tested in the workshop with the pressure condition is still holding, okay, something to put it on record lah. Okay, so well barrier planning is another understanding how to really plan for a barrier that you want to install. You see, you have the drilling phase, you have the production phase, you have your well repair, the well intervention phase, and then you have PNA phase. You have these phases that must have a better planning, understanding about what are the criteria for the barrier for that kind of situation. And is it going to be like a certain barrier, like solid barrier or cement barrier? Which one is considered long term, short term? And then which barrier is considered, reliable barrier? And then how you're going to test that? So it's going to cover a lot of issues. Then normally, if you have the good BIM system, well integrated management system, it will give you some guideline or some, understanding about what are the right proper procedures to set a barrier, to test the barrier, and to record such barrier. Okay, so that's talking about planning. You have the barrier philosophy standard coming up from your standard, the API, so on also, or even Petronas PP Go. And you have to establish a certain criteria for those barrier. And once you comply to there be some of the authority, technical authority that sign in, then you have the confidence that it will be properly checked, then properly considered as a valid barrier. The failure that happened later on is totally different because what happens is that when you do the planning, you do the execution, you do the installation of barrier, it's being checked, being verified that you have done a good job, and then the potential barrier is beyond our control. So that will be part of the requirement to monitor the barrier to the WIM system. Okay. So web barrier schematic. This is always issue for us when we are in an early stage. We don't have the system to record those barrier in time. So whenever somebody do a repair, for example, we have one well, we have well A, we have completed the well A, and then approaching the well, and suddenly maybe after 1 year, there is some requirement to isolate certain zone, because they want to to produce from one particular zone, so they want to stop one of the flowing barrier between the string. So they're going to install some sort of like they close the what they call it the side sliding door. The side sliding door will be closed so that they produce from only the bottom part. So when you see that drawing there, when you do the shifting is done only with the straight line, only with the straight line. So straight line, you just call one crew and you do the adjustment and you close in. But the problem is that there's nobody updating the schematic drawing. The people in town have the old drawing, nobody update the drawings. Then when we come in again, we are coming up with the assumption that it's going to be like all the sliding door open. But when we come in, it's not open. So there'll be some issue like hydraulic trap, and then some of the reservoir that is being left behind, actually coming back to the original pressure rather than depleted. So we open up the barrier, slide door, then we see the pressure is higher than what you expected. Then we might have lost control, based on that unknown data that been not properly stored. That's why the WIM system help us to really monitor everything, even a simple job. It must be uploaded, updated, so that every time we have a perfect new information, latest information about the well. So it reduces chances of failure. So that's on the planning. Okay, for the planning, I think we have one more. I think there's another one coming in up to number 9. So number 3, barrier selection. Okay, primary barrier is to withstand pressure, and then included cemented casing, production packer, tubing, and so on. And then secondary barrier, you're talking about barrier that backup barrier. If the primary barrier fail, then they will come in lah. The column annulus, then safety valve, and so on. So you can see that some of the well, when you do the well intervention, the safety valve become the temporary barrier. But for long term, sometimes this safety valve is not considered as barrier anymore. So it depends on what kind of phases you are in. And normally the WIM system will classify that into a different category so that you understand when do a certain job, what is the status of the barrier. Is it going to be temporary barrier? Is it going to be secondary, primary, or so and so on. Okay, risk assessment. Risk assessment is done to help the engineer, or even to put in our bin system to understand that what are the potential hazard that I mentioned to you. The well is producing and the pressure is declining. Temperature remain the same, but pressure is declining. So some of the safety factor is reducing as well. But of course, with the reducing pressure, then it's much more manageable. So you have to look at all the scenario, recalculate your condition or your safety factor with the declining of pressure and so on. So that's why, so for example, some casing having eroded, the thickness reduction is about 1 mm per year. So you expect that after five years, the reduction in collapse pressure and the burst pressure will be about 30%. So because of the reduction in pressure, maybe that is considered as still valid, and there's no need for repair. This kind of situation or discussion to be verified by survey to make sure that your thickness is still within that range. Operational procedure and verification, you have to define, all this procedure, verified for this procedure that you have, the validity of the barrier and the testing of the barrier. So normally we actually monitoring method. Normally nowadays we have a lot of sensors that we can put in the well so that you can monitor the vibration itself. You consider about the corrosion rate. You consider what are the flow phases that going through, and all this going to give us some indication about the integrity of the well, especially the corrosion. We normally we run this is thickness survey on each tubing. As normally the corrosion is happening at the top 100, let's say top 1,000 meter lah, 1,000, let's say 1,000 meter from surface, where it's going to be the high tension area where erosion will be more with the cable running, and so on, with production, with the environment. So normally we check the top part and look at the corrosion. Normally we can see the trend. The corrosion normally become worse at the top most, and getting less and less at the bottom. So we can make assumption that anything deeper will be much more comfortable, much more uh, in situ or original compared to the top one. So once you measure the worst scenario, the worst section, which is the top, then you know that the well is still in good condition or not. Okay. Okay, now I think it's about time. So we have a short break, then we continue again. 5 minutes break. Okay? And then try to type in any question you type into your box, then we handle those questions, after the break. Thank you everyone. Jumpa lagi. Morning. Jadi, I think there's one question from Fahmi, talking about, what are the role and responsibility. So I think we cover that very soon. Try to remember, kan? So I think the question is more towards like, what are the area or the responsibility of each person managing the WIM, well integrated management system. I think we cover that. Okay, for well barrier planning, we have to conceive mitigation plan that need to be done. For example, if a barrier failure, so we got to do some well control situation here. As you know, when we talk about well integrity, we're talking about preventing hydrocarbon leak. So if there's any leak of hydrocarbon, if it is small amount, normally you can kill with bullheading or maybe just circulation with the kill man. But if it is a big flow, and then if we have some complication like losses, then you have to have a proper well killing procedure that you need to kill them. Of course, when you talk about this situation, we have to different category, different phase or different time. Drilling phase is different when you have all this situation of failure, and then you're talking about producing well, it's different. And then we're talking about the well intervention, well repair will be different. And then when you have your P&A, the contingency plan will be different in terms of managing the hydrocarbon. Of course, like when you talk about P&A, the well is almost dead. There's no more, we call it commercial value, and the gas is all depleted. So we are dealing with losses rather than flow of the carbon. Even though there will be still some requirement to understand what are the contingency plan in case you have to control the well and then you have losses. Of course, there will be a few technique in well control certification study, or when you go for test for well control, you have that understanding about how to manage well control with loss correlation. Of course, at the same time, competition is also there. When we talk about controlling the flow of hydrocarbon, we're talking about well control. Well control, normally, because of the different situation, when you are drilling, there is special IWCF or IDC well control school dealing with only drilling. And then, of course, there also another special well control school dealing with the well intervention. So it's different understanding about the situation of the well. And then, of course, how to manage the well control with this different environment. Kan, for example, kalau you drilling a well, talking about open hole, kan, you drill, you have your cemented casing, you drill open hole, you have a kick, then you have to manage the weaknesses of the open hole, plus your weaknesses of your casing, if any, and then even your surface equipment. But when you have your well control, well intervention, you see it's different. For intervention, you have all your casing be tested, intact, you have your tubing, and then you have packer to isolate your pressure, and then you have open preparation, linking your pressure between your tubing, and then of course your pressure in the reservoir is depleting, and sometimes you have some plugging, so all those kind of things that will be different of controlling the well control for the producing well and also from the drilling well. So the communication, the documentation and change management is always be the same thing, like to apply whatever changes in your original plan, and MOC will be used, because MOC will be used to really make sure it's all been done properly. You have completed your risk assessment, you have your contingency plan, then the approval will become in to implement the MOC. And then for audit, of course, they have to really do some periodic check on your audits. That's why the WIMS will help a lot in terms of having the update up to date. Even some WIMS is linked to the what I call it real-time sensors and so on. So you can see the development of pressure in your casing, the downhole, and then even you can consider like what are the phase coming up, 2 phases or 3 phases of flow in to your flow line at the top. So all this information will help you to understand what are the situation on the well in terms of the corrosive environment, the vibration, and so on. Okay, now we go and cover the well integrity system. This is the subject that we discuss more about how this application will help us to really manage the well integrity of the well throughout the well life. So we're starting from, even if possible, we start from drilling a well. We start to record the information on drilling a well, how they do the cementing job, where is the top of cement, and then how the casing being placed in place. You're going to be any torque or any obstruction on going down. So all this will help us to really improve our understanding about the well integrity, from drilling, say. And then once you completed drilling, you have it on production. Of course, they will continue recording the vibration, the production of the well, the vibration, and then they can shut in, the shutdown. All this record will be helping us to understand how is the health of the well. So WIMS actually is like a medical certificate. So it will show you your heartbeat, your rate, your kidney condition, your liver, and so on. It's just a similar situation. We have a well, we have to monitor the health condition, and we do the medication as required. Okay. So in general, you have a manual for WIMS. It will relate to the application. So in the manual, we highlight the objective of the WIMS, more or less, and then the three pillars of WIMS, talking about the technical and the orders management and so on. And then the requirement for team. So this is the team where the WIMS we ask us to really implement a team. Now, big companies, they have a special well integrity team or department. So well integrity department sometimes is under safety, but sometimes it's by its own. So well integrity department, we have the proper team. They will hire, all this category of people that need to be able to do monitoring, to do offshore, to do the checking, and how to manage contracts for the third party and so on. Competency, the team need to be strong. If there's any weaknesses or any gap, then of course we need to hire the third party on a call-up basis or whatever, or maybe having a third party to really run the system itself. So it depends on, if you're a small company, then always important to have a third party coming in to help you. And then of course the rest will be on the training program for your team to get familiar with the system. Roles and responsibility, it will be outlined. The reason is purely because we don't want to have any confusion, overlapping, or misunderstanding about role. Because without the role and responsibility, normally it will be like, people say that it's not my area, then suddenly another people say that it's not my area, so we have a gap. Then it becomes an issue. So role and responsibility, avoid those gap that may happen, and then give the understanding of who's going to be acting directly to the situation and going to be on backup, on management, and so on. So elements of WIMS, normally they will cover what are the requirement for the WIMS in terms of the security, the checking, verification, and so on. So the toolkits, normally the WIMS will have the toolkits like having the graphics drawing, a database, a learning curve, all those kind of additional toolkits attached to the WIMS. Even some of the WIMS can be connected to most of the NTW report, so like completion report, completion drawings, any wireline job. So it's possible to have all the possible link to the application, for records. Common features, normally we try to make sure that every format will be about the same, so easier for people to understand. So we are dealing with drilling, you're going to have different drilling well integrity. Producing will be a different, and when repair, when intervention will be different as well. So codes normally will help us to make people consistent with the job assignment. That will help us to do the proper timing, coding in terms of the lesson learned, and try to see what are the area that needs to be more attention and so on. Well schematic always be important. We have a well schematic for drilling, for completion, and then it will be updated. So sometimes you have original completion drawing, and then you see the evolution of that completion drawing as we go through a system of well repair, the recompletion, and then suddenly you go to walkover, recompletion, then suddenly you have hydraulic walkover, all this, or hydraulic fracturing job. All that will be captured with a different schematic if there's any change. Sometimes they change the configuration by putting in certain element. like they cut in the top part and then replacing the triple SV with a new sub assembly, top assembly, and so on. So the schematic will change with time. So it's all been recorded properly in the application. Assessment flow, normally if there's any audit or any assessment for the well integrity, then of course we want to see the understanding about the proper check that should be done, rather than random and then you miss some of the key point. Key indicators normally like KPI, lah. So we try to see some area, they record some of the life of the, for example, the wing of the gate valve. Normally, after certain rotation, they see that the potential failure of the gate, and then of course some of the, for example, triple SB, some triple SB after doing some manipulation of the valve, they start to see indication of failure after the 20th test or the cycle and so on. So it's all be the key indicator on the key element in the combination string itself. Okay. Vim software, the features, and then the element log that is being shown in the content. How you're going to record the event log, the sample, potentially pass, or the recording that should be done. I think we have few same. Okay, maintenance, high risk well management. All this is part of the WIMS, and then commercial level WIMS. I think we're going to cover that. That's the content. So set up WIMS, you can see that when we want to set up a WIMS integrated system itself, it cover a few workflow. No? For example, well, the manual itself will have integrity guideline over there, and integrity guideline we have a few volume to handle the monitoring, the annulus leak, the competency assurance process, and then well maintenance. So every chapter will explain more details about how the WIM should be used and how the system is able to help you to identify potential failure and so on. So set up WINS. Objective of the WINS, normally you know that is to give a transparency of how risk is managed and to benchmark against other operators. So the moment you have the WIMS system, normally they have a consortium of, we call it user itself. So the original company that sell you the WIMS will coordinate a meeting with other operator. So you try to share how each operator managed to fully utilize the system and how is going to be the tricks and the guideline that had to be changed or improved. So that's only once you're in the WIMS, you have a consortium of those users for you to discuss about the best to really fully utilize the WIMS. Okay, so integrity team, you can see like Fahmi, if we talk about some of the team over here, you can see we can have the corrosion engineer is part of the team. We have the well integrity authority, which is the SME, to really look through all the system. You have the team leader, you have coordinator, and then for continue, of course, below the coordinator, you will start to have all these project engineer, well, the supervisor, and so on. So normally you see that since we are talking about WIM itself, normally we cover up to project engineer and well engineer as the, hired by the company. But normally for the well intervention technical engineer, normally we can start to look for the third party services that perform the integration. But if you are big enough, some company big enough, they have everything in their department, so they will have their own independent check for the team. So the team can be fully like this for the big company, and you can be half. Another half will be more on call-out basis or on ad hoc basis, depends on your requirement to perform well integrity check and so on. So all the special review audit only done by third party lah. Okay. And the elements of WIMS. So element of WIMS talking about quite a lot. So in this case, the ownership over the life cycle, they're talking about from exploration development. Normally exploration, normally about one well, then they be just abandoned. So it's not much on the well integrity. So the only thing that your plan A for well exploration well must be done properly for a long term. But once you develop the field, and then you produce the well, then going to be a few category of how to manage the well integrity, suspended well, and then you have idle well where you have your shutdown due to some failure or some mechanical issues. Then the well should be still under proper well integrity to be able to be on the suspended mode, idle. Isolated means that you isolate certain reservoir and you keep the well for some time. So you must understand that there will be two barriers to be able to leave the well for, until you have your conclusion to repair or to re-enter the well and so on. So close-in well, well production, well abandonment. That's the ownership of each one, life cycle. Organizational structure with rules, you have to do that. Risk assessment have to be done. Well types with well barrier. So we have different well type with different well barrier. Water injection, we have a different barrier. Gas producer will be a different barrier, and oil well will be a different barrier because of the different flow and pressure system that they have. Okay, so performance standard, of course, it's quite normal. We have the standard for each beams. Well barrier verification, I think more or less by checking again, the barrier condition, verification, approval, and so on. So underlying process is normally like once we all have done a good job, you have to do a proper reporting, put the documentation properly in your database, and record your management of change so people can see and then try to more or less, follow the step or suggestion when we have the same issue. So continuous improvement is always important, especially when you have a group of experts discussing about the better improvement of those VIMs. Then you are learning from the expert. Then you are going to be better for the company. So auditing always be an issue. Auditing go back to whatever you have done. They will most or less comment on your system, your weaknesses. So like for example, you have less meeting on well integrity with your staff, then it's no good. There are always some requirement that you must also spend some time going offshore, try to discuss with the people on site, understanding what are their concern and understanding what they are missing. Sometimes they are not aware of what need to be done. So by visiting to the site, you have to have that sharing session. They will give you information, you give them information, so you improve the system by itself. Okay. So the toolkit, I think we're talking about the toolkit, this is a lot. We have in the Vim system, we have the well failure model, we have the well design. Try to put in the well design when during the drilling stage. When they completed the well, we understand that the well we designed with the casing spec, and then they have the material selection for the casing, for the tubing. So it'll give you some idea about the well has been prepared for the best. But now when you are going in the production phase, this is where you're going to more or less continue with the confirmation of all those strengths and weaknesses and see where you are, whether you need to do some repair, some changes, and so on. So as you go, the production management will have the production data showing the water content, the water production that is coming in. You're going to be a production data with pressure and temperature coming in, and lower and so on, whatever. So this is annual pressure management will happen also over here. When we have the completion data, of course, you have to look at the annual pressure with the maximum maintenance surface pressure. Is one of the key to monitor the stresses at the surface around the wellhead area. And then preventive maintenance, you have to do some preparation. Sometimes you have seen that when you do a preventive maintenance, you want to do it in batches, for example, every 6 months or every 1 year. But some of the components have to be maintained almost every month. So in other words, your preventive maintenance schedule can be minor or can be major. So we have to really decide on the strategy of this preventive maintenance. Some will be done on monthly basis, some will be done on the 6 month basis, or sometimes it's been done on every 3 years, for example. So it all depends on the reliability of the equipment and the records and database from all over the world that some equipment is reliable to a certain phase. So you should have that the information as part of the VIMS record. Maintenance result, you can see that how you see what are the failure that come in earlier than expected. Or sometimes you can see that some of the maintenance can be rearranged. Rather than do it 6 monthly, you can do it every year, for example, because the quality of the integrity of the material is so good that you can even space out your maintenance. So role responsibility, so same thing. What should you do? For example, role responsibility is more to like, if, for example, you have failure in the wellhead. So you want to know that only the wellhead people will handle that. You don't ask the wireline crew to come in and then try to check the wellhead. So it's not the right true. So you have the proper role expertise to do the repair job. Okay. So that's the toolkit. This is an example of well barrier schematic. So barrier schematic can see that when we draw, like I mentioned to you, there's always an issue of updating. we have the people offshore have different drawings. So when the wireline crew come into the offshore, they look straight away to the site or the data which is not updated. So normally the crew must go to the HQ, and the HQ should be able to update. And sometimes the HQ also have not updated information because all being done offshore is updated offshore, and there's no communication. You are in trouble. Communication breakdown. So we're always looking for the most updated well barrier before we do the subsequent job. Okay. And then, of course, it's always good to have a barrier schematic, because now become a part of the WIMS. They will try to give you an indication of the barrier in your well bore. Some barrier will be defined as secondary, some will be defined as primary. So this is where they will record, and then you understand which one is the important. The last line of defense is the primary barrier, and you have secondary barrier to make sure that you always have option. If the failure of primary barrier, you have another option to do subsequent job rather than having a surprise. So you always have contingency plan in place now with secondary barrier. Okay, that's how it looks like the drawing. Secondary barrier also the same thing. Sometimes you need to be updated after a few series of well intervention, a few series of major work. Then you're talking about upgrading the schematic. But you just doing the wireline job. You're only touching the valve here, wireline job, or the valve here, but nothing outside. So you're talking about only the integrity of the tubing, the triple SV, and then maybe some of the packer, the bottom hole assembly. So not much. Okay, well, integrity checklist. We can see that there's a list how we're going to deal for wellhead, for monitoring. So we're talking about to see a leak over there, and this if no leak, you put a no leak. Then of course the acceptance for going to be different. Okay, sorry, macam mana? Terkeluar. Angin nak keluar padam. Sekejap. Share balik. Ada. Okay. Okay kan? Okay. Okay, now I think we go back again. This monitoring system, you can see that we had wellhead trees at the different category. Okay, we have about the operability, the activation, the leakage rate, and then the integrity of the valve. So we start with inspection, operability, how we going to operate that? Is it going to be very tight, loose, and so on? Activation, how activate. If it is air driven or hydraulic driven, there will also be an understanding about how the activation. For example, some of the activation might be within 30 seconds, for example. So you have the hydraulic valve. So you test it according to the spec. It should be tested. Should be closing within 20 minutes. Then you record. If it's 30 minutes, it's a failure. So they have to do some repair job. So there will be another work scope that be repair work if it is not achieving the acceptable closing time and so on, or pressure. Okay, the next one is annulus integrity management. So we have to understand the limit. I think I will show you before this closing down. I will show you how actually we managed to identify the limit of the annulus pressure, so that we are not going to go beyond that. Otherwise, we start to maybe cause some failure of the casing, bursting the casing, and so on. So acceptance test is also there, and then of course you have a few items here. Pressure testing those valve here, and then try to see the pressure reading, the limit of the pressure in the annulus. Subsurface safety valve is also important. We have to do some tests. Normally during installation we do one test, but after some time, normally during the special case or audit maintenance, we try to reactivate the safety valve just to see the direction itself. How much liquid, how does the fluid we need to ready to open up the safety valve is all being recorded for the leak. So leak, normally if you close, sometimes there's some seepage from the space, so it must be a certain limit that you can accept. Otherwise, it's considered a failure. So there will be a change of this triple SV and so on. So yeah, gas leak valve check, and the hanger neck seat is that top surface. So one is leak, you get to expose directly to the hydrocarbon to the surface. So it's quite important as well. But normally we can have the triple SV close so that we can do the repair of this neck seal. Okay, by installing the bridge plug and the wellhead, and then the two-way plug, called the solid plug, and then we can close the triple SV and of course they have two barrier temporary to do repair. Okay. Safety operating envelope, normally they try to record. This all the WIM, so you can see that, how the pressure, temperature, fluid risk, all they will be recorded for them to flow the well. So like I mentioned, if you operating the well with a high flow rate, and then it's decreasing, it's acceptable. But the problem is that sometimes decision is made to increase production of that well, and then you might see that the changes in the environment, the fluid flow, the cooling effect, the temperature effect itself will create a different stresses to the bowl, and you have to double check again. So that's why we understand about the safety operating limit based on the calculation, and then when we have the real situation, we have to double check again to see that the well is still in good condition. The challenges, normally you can see that, challenges that we are talking about here is that we go back to the world, see what are the common failure for barrier element throughout the world, in terms of North Sea, the Gulf of Mexico, in terms of anything to do with Southeast Asia, and there's Indonesia, Australia. So we take out overall. So you can see that the highest so far is about 38% tubing. Tubing failure is there because tubing is the one that always being exposed to the corrosive production of crude oil. And then tubing experience movement. You shut in the well, you close in the well, actually you put stress because you are tubing the pressure down, up. So tubing start to really move up and down. And then even when you flow, and the flow is not always consistent. Sometimes high flow, low flow, so you start to vibrate. So tubing is much more exposed to vibration and then stresses and so on. That's why you can see the failure of tubing is a lot. So when you have tubing failure, you're talking about losing a main component because a barrier, tubing can be considered as a barrier because it's been tested. So the one if you have the failure, then you're talking about repair. And repair for tubing well can go between 5 to 10 days. It depends on the complexity of the condition. So 5 days you might lose, means a lot in production. If you produce one well 5,000 barrel a day, so 5 days you have 35,000 barrel being lost, which is close to a lot of money as well. Okay. Now there's the second item that is going to be on the conductor. Conductor, because it's exposed. Conductor is the first casing that we run, and then that is the first casing that is exposed to the marine environment. In Sarawak, I've seen that, this when we go in and take over the shell well, categorically take over the shell well, the well had been there for almost like 20 years. You can see the corrosion on the conductor is almost gone. It's very because of that environment. But the casing inside start to have an intact because being isolated for some time. So the first conductor will be much more damaged. It has lost the support. So the casing or the weight of the casing and the string have no more support because the conductor now it start to move down. Okay, another safety valve, as you know, is going to be a triple safety valve because it's one of the item is part of the tubing string is being exposed to the flow of the hydrocarbon. You have the fluctuation of pressure up and down, low and high, and then you have some sand going through, so it start to really cause problem with the annular safety valve. Okay. Casing, because of I think it go back to the conductor, the top part of the casing also being affected by corrosion as well, mostly. Wellhead, of course, wellhead is 5%. The damage of wellhead only because of the, we like the same, the fluid coming in is quite abrasive and then corrosive. At the same time, wellhead, only we open up and or close the wellhead to manage the flow and so on. And then, of course, the wellhead is in a holding position where you're talking about most of the debris will be there, and then some leak because normally some of the packer element within the wellhead actually will last about 2 or 3 years. Then you have to replace the sealing in some cases. But nowadays we have metal to metal seal, which is going to be helping a lot with the life of the wellhead. Well designed also the same thing. Well designed talking about everything from the casing, the tubing, as well the wellhead. So it's more overall. Okay, so let's study. Tubing is the worst. Now cementing job failure, because when you talk about well integrity, if it is drilling, you have your cemented casing before you drill open hole. When you have production, you have your cemented casing around the tubing, and of course, it should be more or less sealed. So if okay, let me see. Okay. So of course the cement itself should be doing the zonal isolation. So if you have a good cement like this one, you can see that you have the annulus seal around the casing. So if it is, for example, 100 meter, 200 meter of this seal, then it's going to be a very good seal. But sometimes because of the cement is not going to the top, so most of the uncemented area we have going to be mostly exposed to the fluid. But normally we will have to have more cement above the hydrocarbon area. So this is mostly above the hydrocarbon area or inside casing where there's no cement. But even in the production hole, we plan to have a good cement around, but sometimes what we have is only a portion, only uncemented portion because of the fluid flow. Because when you pump cement, the cement will try to flow into the easiest path. So when easiest path is coming to the top, it will go up. Then you have some vacuum or some a void at the bottom. That is the channeling effect. So the gas can still go into to behind the casing. So in our well, what happens is we have a 1,000 meter of section. So we have a cement from the 1,000 section. You can see some portion will be good cement, some portion will be bad cement, but overall, each good sealing will be able to help to isolate the uncemented part. So in overall, sometimes we can see that it's still a good cementing job, even though some portion, 20% or 10%, 30% is still uncemented in certain part. So as long as it's not exposed to hydrocarbon, we are okay. Okay. So in terms of cement failure, job planning is about 30% failure. Say the most. If you plan the job improperly in terms of the pumping, establishment of cement, the mixing of cement is not right, and then the centralization of cement is bad, then you're in trouble. 35% failure because of poor planning. Special design should be able to clean up, all the mud cakes and so on, before you have your cement touching the formation. So actually, it's like a cleaning process before we put cement. So special design, if it's not proper, it's not large enough in terms of volume, you have the failure as well. So this is the statistic of failure of jet cement, recorded worldwide by the cementing company. Okay. Now we have triple SV. Another issues, like triple SV, we have to final test every 6 months as per the API, and then the leak rate is 400 cc. So you imagine that when you want to test, you have producing the well, let's say the oil well, you close in, and then you see you open up top so that the pressure will try to push from bottom. So it's like it's no more pressure at the top, only hydrostatic or the oil column, and then you want to see the leak. If the leak is more than 400 cc in a minute, it's considered a leak. If it is gas, it's 50 standard cubic feet per minute. You try to record the volume. So if it is more, it's considered a leak. Then you have to do a repair job. But normally this is, if you say, for example, the limit is 400 and then you have 500. So you say, well, it's a failure. But sometimes you say that maybe you're allowed to produce for another 1 week or 1 month before you do the repair job, But normally, some companies say, no, when you have a limit, stay to your guideline. Unless you have MOC to do that. So it's all legal. Okay. Okay. Now the question, let me check the question. Okay. Is it, let's say our drilling path. Is that the one? Or you have something at the top? Azami, for operating, please join. Okay, I think that's the question. Okay. The question is, let's say our drilling path getting deviated away from vertical to horizontal when the drilling got deeper. Okay. Do we still case and plug in regards to the direction of the path? So this is more a question like, no, we are deviating from our target. So the situation is like this. When we drill a well, we have a target section. For when you are drilling, for example, you are getting close to the target and suddenly you are away from we call it target radius. So the target radius might be about 50-meter radius, and you are outside the radius, and maybe you are 100 meters away from the radius. So in this case, we normally, before we reach to that situation, we already decided whether we have to plug in the well earlier or then subtract to the target required, or we accept that position. Normally, we will go back to the before. For example, you're about 300 meter from your last depth. So when you are away, then and then when you do the projection, you say that I'm going to be 100 meter away from your target area. And then we talk to the geologists, the reservoir, they decide is it going to be acceptable or not. If they think that it's critical, and then you're going to be in trouble. They have to really plug in whatever you have drilled and do the sub tracking earlier. If you don't do the sub tracking earlier, you're going to still miss the target. Okay, thank you. Okay, now triple SB, at the same time, we talk about casing pressure. Casing pressure is always a nightmare. We want to understand how we're going to manage that. It's going to be issue. So casing pressure, normally you have your casing pressure, you can see from top. For example, this is your tubing. And then behind tubing is between the casing, production casing and tubing is called annulus A. And then to the production casing, and then from your intermediate casing, it's called B. And then from your intermediate casing to your space casing, called C lah. So when the problem of having this pressure, because it's supposed to be zero pressure, because we have all the hydrostatic pressure, key pressure done. So normally A will be zero, B will be zero, C will be zero. But because when you set all this case, all this wellhead here in the cold temperature, in this, when you pump in or you install, that's why the pressure is zero. But the moment you have your production coming from below, is heated. So you start to heat your tubing, and you start to heat all your annulus pressure. So you can see that the heating will start to cause the pressure to increase because hydraulic pressure increase. And then the heat also will start to be transmitted to the next layer, next annulus. So also then we're going to have some pressure increase. So this pressure increase, normally if we know that it's just because of thermal, then we can bleed off because it's thermal expansion. But now you can see that if it is not because of thermal, because of the potential leak from the formation here, if the oil is the pressure is coming here, for example, the hydrostatic here is 1000 psi, but the pressure here is 1100. So 100 psi here, we start to have the bubble oil or gas coming in, and that we start to have a pressure of maybe 1000 plus. So we have the pressure increasing at this point because of the communication between reservoir and the annulus. Same thing like B, if we have some pressure coming up from shallow gas, from the water zone, then you start to recharge your pressure. So understanding the source of hydrocarbon, if it is water, normally you bleed off, no issue. But if it is gas, when you bleed off, more gas coming in. So there will be some limit that you will allow so that it start to stabilize. So this limit have to be computed. Okay. So the root cause of this second, so this is more or less the understanding. Of course, production casing near surface start to have problem because some of the casing have been intention and compression, and because the corrosive environment at the top start to have some corrosion at the tip, connection here. There's also maybe some pitting lah over here as well. Jam out much. Corrosion in tubing, like we discussed before, because of the production coming up, because of abrasion from the sand, because we have some bending stresses. So when you have the tubing leak, corrosion leak, then you have to do a walkover, pulling out tubing and running up with the new tubing. This is another case. So what I normally do actually, you have a packer here. So if you have a stringer here, you normally can unlace. So you break up the tubing up, and then you come up with your overshot. You try to pull the stringer. Sometimes they have we call it the pin, the safety pin that you can pin out, and then you come in with a packer. You swallow it over here, and then you continue producing. Something like that. For the middle job. Okay, this is the example that I show you, the surface casing corroded, like my experience with the Baram Delta. After 25 years, most of the casing corroded. You have this is your conductor casing corroded, and your surface casing. It's also getting worse and worse. So, and then it's through assurance, because once you have a scale coming in the tubing, this scale sometimes it start to really not only put up scale, but it start to eat up some of the metal. And then it causes corrosion. You have your parted coast tubing here. But in most cases, what I've seen in our well, we have barium sulfate scale, which is like cholesterol. It start to really fill up your tubing, and then it getting less production, less production. You think that reservoir is not good anymore, but realize that you see relate when you want to run a survey, dimensional survey, you're stuck with a small diameter, and it's scaling lah. It's like cholesterol building up in your arteries. So you have to mill. Then once you mill, then you start to have full bore, they start to flow like hell. Okay, that's another issue of skill. Okay. Okay, now let's see the one question. Okay. Sometimes poor cementing results from contamination with formation fluid and drilling fluid. Do we have a standard siphon that will spell minimum allowable level of contamination for successful? Okay. The cementing job, normally what happen, contamination from formation fluid is not much because when we do the cementing, we are in a overbalance situation. So no fluids coming in. But what happened actually, some of the fluid, this is considered here is a gaseous fluid. For example, some of the gas sand have some CO2 that when we do the cementing job, CO2 start to come in and try to really contaminate our cement, So in terms of some guidelines, so if you know that you're drilling to the area, for example, in Sabah and Sarawak, we know going to cement across a high CO2 content of reservoir, then we have to use, we call it a slag-mented cement. It's a charcoal cement mixed with coal, with carbon, and then the carbon will absorb the CO2, and it will help to really improve the properties. And drilling fluid, the problem with drilling fluid when we do cementing is because of when we have interface between the top of cement and then the formation, there will be a mixture, a contamination, So that's why in cementing we use spacer, and recommend to use spacer to isolate the cement and the mud. And then of course when there's a contamination, it's between the spacer and the drilling fluid. And of course the mud and the spacer, so it's still under control. It's not going to be much more problem lah. Even to avoid further contamination, our drilling mud have been tested to make sure it will not affect the properties of cement, even though they are mixed. So that's a guarantee that even if we make some mistake, the drilling fluid will not affect the thickening time of the cement, and then we are still okay with the cementing job. Okay, I think it's Lukman. Thank you, Lukman. Okay, surface casing failure is bursting. At the top here, what happened actually in this well, I think somewhere in the North Sea, Alaska. What happened actually, they have a trap system where the cement, the casing here have a seal here, and then they don't have the valve can be plugged above. So when the temperature of production coming in, it start to really put on some pressure to your annulus trap area. So in the trap area, the hydraulic pressure will go high. Even though it start with 100 psi, with the expansion of the liquid hydraulic push, it can go to 7,000 psi, and it bursts the surface casing. So they can see very far at the top, because that's the weakest point at the top. So that's why you can see that annulus pressure actually can create problem. But for us, for offshore, what we do, all the casing annulus here, we have the gauge valve here. So we open up the gauge valve, so the pressure will be readed up here. So for example, the pressure, normally we put a pressure gauge of 2,000 psi, for example. So if the pressure is going up beyond 2,000 psi, it will break up the gauges. So automatically become a relief valve, So that's how normally what happen. We don't see this situation in our field because mostly we are installing mostly the gauge valve on each valve. So if there's any high pressure, it will burst the valve itself or our metering, our gauge. Then we have to bleed some of the pressure lah. Okay. And okay. I think the rest is just matter of barrier diagnostic is all additional information. I think we're going to share this information to you through our video. I think from our slide. Hopefully that will help you. So it's just matter of repeating again some like annulus pressure, how we're going to manage that pressure, and to record, and they will help you, to limit your pressure, understanding your requirement to monitor the annulus pressure on each well. we cover most or less the most of the topics, especially understanding about well integrity. As we go through, like I mentioned to you, WIMS application helps a lot to really normalize all the previous issues and problems that we learn. Our lesson learned is that this is so important. Without application, we are going to lose our documentation, our facts about OSHWEL, and then miscommunication will happen, and I think about error will happen quite common. So we need WIMS to be able to make sure we do the job properly and professionally. Okay, thank you, and see you again some other time. Assalamualaikum.